Hi, my name is Ramkrishna Sharma, and I would like to go over a few topics in data structures and algorithms, which of course should not be confused for the same thing. A data structure is a place to hold data, and these data structures differ in how you can add, how you can delete, how you can find, how you can remove. But that is, of course, a data structure. The algorithm are a series of steps to actually solve a problem using the data structure. Today, I'm not necessarily covering data structures, but I'm covering algorithms that will use certain data structures to solve a certain class or category of problems. The first is something called a greedy algorithm. Then I'll talk about optimal substructure with a certain nuance. Then I'll talk about a proof for optimal substructure. How can you look at a problem and define whether or not it has or exhibits optimal substructure? And then I'll talk about Dijkstra, which is a way to find the shortest path if given a graph. I'll talk about its purpose, its key tenets, how to execute it, and how to infer its runtime. I will then, of course, talk about a proof of correctness for how we know that we're making the right decisions when it comes to Dijkstra. So the first thing is, of course, a greedy algorithm. Now, the way you want to understand what a greedy algorithm is specifically local and global. A greedy algorithm will consistently make a decision on a local level, a small decision, and then evolve it to what it hopes to be a globally optimal solution. So the way you want to think about that is, suppose there's a small decision you can make towards a larger optimal solution. A greedy algorithm will suppose that if I continue making this decision repetitively, when it's all said and done, I'd have had a globally optimal result. That globally optimal result would have been the consequence of small optimal decisions. And that is, in fact, a greedy algorithm. Now, one example to understand where you might use such a thing and where the concept of a greedy algorithm might work is making change. Suppose I give you a dollar amount and I say, well, make change for me. How would you do that? How would you do that in the fewest number of coins possible? That's what we're optimizing for. So it's not necessarily the case that optimal solutions are solutions that yield the highest amount. You could, in fact, be optimizing for the smallest. And in the case of making change, when I ask you, I have $5 or $5.32, you have a collection of denominations, supposedly. Make change for me such that the collection at the end is the fewest amount of coins. In other words, there is no smaller set of coins that can make change for the amount I'd like. That is an optimization problem. Now, you might look at that and you might say, well, of the algorithms I know, what do I apply? And you're not necessarily supposed to know immediately, but when you're asked to make change and you say, well, intuitively, if I want to make change for an amount, let me just issue the largest coin I have, and let me do that repeatedly until I satisfy the amount, right? If I can fit 3/4, I'll fit 3/4. I won't even bother with a dime or a nickel or a penny. Let me fixate on the quarters. As soon as putting down another quarter exceeds the amount or overflows, I'll issue the next highest amount. So you can already see why the concept of a greedy algorithm would become intuitive to someone, especially because here I know what decision I should make towards stepping towards the final optimal answer. I know what that decision is. And so you would say, well, okay, I will solve the making change problem, which is asking me to optimize for the smallest number of coins using a greedy algorithm. This is an instance within which a greedy algorithm makes sense. Now, the issue is greedy algorithms will not necessarily always work. For a greedy algorithm to work, it must have a property. The problem must have or exhibit, same thing, a property. And that property is something called optimal substructure. Now, optimal substructure says that if I said, well, okay, I'm trying to make change for a collection of coins, or I'm trying to make change for a dollar amount, and this, in fact, here, what I have here, is the answer. Optimal substructure says, well, you should be able to look at this idea here of the coins you have at hand, and you should be able to peel off just one from that problem, from that solution rather, from the solution set. And this, in a sense, should be the optimal solution for whatever this is now, right? Let's say, this was the optimal solution for making change for, $2.30. Well, let's say I just removed a nickel. Now I have $2.25. So this, in fact, should be the optimal solution for $2.25. Now, of course, 3 will certainly not satisfy that. But you can understand that the moment I remove something, I should be left with the optimal solution for that version of the problem. So put more concisely, optimal substructure is a property of a problem where the solution can be seen to be made up of smaller optimal solutions of the same problem. But there's a nuance. There's a nuance. The nuance is you can't solve subproblems optimally and then combine them for a globally optimal result. It only works in that sense one way. In the way I've just illustrated. You can't just make an optimal solution for this and an optimal solution for this and then combine these and say, well, this now serves some larger aggregate optimal solution. That will not work. That simply will not work. So that covers optimal substructure from a theoretical sense. And that's important to gauge, especially if greedy algorithms are what you're trying to apply. You say, well, I'm trying to use a greedy algorithm here. Does this problem exhibit optimal substructure? Now you might say, well, I don't know if it does. How do I know? Seems like I have to do a lot in order to just get to the point of figuring out the solution and then looking at subproblems within that solution to understand if a problem in fact has optimal substructure. But as it happens, there is a proof for optimal substructure. What you do in terms of what I would consider to be a template for solving these optimal substructure problems is assume that you have some set C where elements in this set, right, C1, C2, C3, C4, all the way to Cn are elements that contribute, in this case of making change, to the answer, A. And so in that sense, C is the set that leads us to an answer overall. You can think of this as a set of coins towards the optimal solution A. Start with that. And of course, recall what I said about removing an element from the optimal solution set. Then what's left should be an optimal solution for that version of the problem. In that sense, C prime, C1, C2, C3, and I'll C4, all the way to Cn minus 1. In other words, there's just one element missing from this set. So I took the optimal solution, I peeled one element off, and here I have a new set that is absent of one element. Now, this should be the optimal solution for getting to A minus C1, you can imagine. because I said if you peel an element off, what's left should be an optimal solution for what that answer represents. So if I had A before and I remove C1, well, then it should be A minus C1. And what's left in the optimal solution set should in fact be contributory to the answer. Now, as it happens, because we're going to structure this as a proof by contradiction, we say, assume C prime is not, in fact, the optimal solution to make change for A minus C1. Suppose it isn't. Well, trail that logic through for a moment. If it isn't, well, then there must be some other set, C prime prime, just to be able to distinguish between all the C's that we have on the board, that is able to make change for A minus C1 in less coins than what C prime did it in. In a sense, now, these are competitors. We said that we have this set C within which we have elements that contribute to the solution A, and that A, what these elements produced, being A, are in fact the optimal solution. And we said, well, if that's true and the problem exhibits optimal substructure, then I should be able to take one element out so that now I have everything I had before with the absence of one element. And that should, in fact, be the solution for its own version of the same problem, producing A minus C1. Then I said, well, assume that this C prime is not, in fact, optimal, in which case C prime prime does it better than C prime. It does it in fewer coins. So the way you want to think about it is, if let's say J represents the number of elements within this set, then J is less than n minus 1. I say J is less than n minus 1 largely because n minus 1 were how many coins it took to solve optimally A minus C1. And so if C prime prime comes in and says, well, I can do it better than A minus C1, then the elements within it, J, should be less than n minus C1. That's the only conceivable way in which C prime prime could have done it better. And so, naturally, what you do now as part of this proof is you add back the element you stripped off to get C prime. In fact, this should probably be, some C, not necessarily C1, but C naught, right? Any kind of C that you've stripped out, or, let's just say it's CX, right? Because C1 actually attributes to the first element, and we haven't kept it consistent of that being stripped off. So CX is just what we stripped off, right? So originally we had A, and then we stripped CX off, some coin. And now let's say we add it back. We add CX back to C prime prime, which is supposedly the set that has been able to solve this problem for A minus CX in less than these many coins, in less than n minus 1 coins. So we add that element back, and if we do, then you actually don't have just J coins anymore in the set C prime prime. You have J plus 1 coins, and of course we know that if we add one on this side, we must, of course, because it is an inequality, we must, of course, add the same on the other side. But this is now interesting. J plus 1 is less than n, which in a sense means however many coins are in C prime prime, it is fewer coins than n. Now that ends up being contradiction. Because C prime prime, because if you ask yourself, well, what's the value of C prime prime? Right? You had A originally in the original set, and then C prime prime is A minus that one coin you stripped off. But then you ended up adding that 1 point you stripped off. And so C prime prime and C prime prime, CX and CX cancel out. And so basically this set, C prime prime, consists of j plus 1 coins, which are still less than n coins, and yet we've gotten a as a value. So let me make a headline here. The headline is, this other set, C prime prime, has made fewer coins, has solved for A, the original problem, in fewer coins than what we said was optimal. We started the chain of logic by saying that C will produce the optimal solution in n coins for A. And yet now, we say this other amount, which is less than n coins, can do it better. And it can in fact resolve to A. Now that, of course, is a contradiction. If we said this was the most optimal, then how come now, after everything we've done, we produce A in fewer than n coins? Then, of course, it must be the case that what we said before was true, because the chain of reasoning we've had to follow produces a contradiction. If something is true, then the conclusions based on it, if they're sound, will be true as well. And so that is how to prove optimal substructure, which is, of course, a pattern that we will see continued in several things, right? We'll see, when we're trying to understand, well, is a particular algorithm that is supposed to solve for a tree, is that optimal, right? In fact, what we'll do in those cases, does it exhibit optimal substructure? We'll always start with a set that contributes, that has elements in it that record or that lead to the end result of an optimal solution. And then we'll strip one off and we'll say, if it's true that this problem or this solution has optimal substructure, then I should be able to strip one element off from that, and I should be left with a version of the same problem for which A minus that thing I stripped off leads to the optimal solution. And then I'll negate that. I'll say, well, assume that's not the case. Assume C prime prime is a more optimal solution. And C prime prime can basically do it better than C prime. It can get the same result as C prime, but better in fewer things. And then you end up adding that thing back invariably. And when you do eventually add that thing back, you find that you've solved the overall problem more optimally than what you originally suggested, which is in fact a contradiction.